Two random variables walked into a bar, but they thought they were being discrete, but I heard them continuously chatter. Get it? Discrete and continuous? And we are talking about random variables today. So let me just ask you, what's fair? You and your friend wager on heads or tails. If he bets $1 on heads, what is a fair wager for you to make on tails? Well, heads, he's going to win, right? Tails, you're going to win. Payout, so if he gets heads, you lose $1. And the probability of that is a half. So we're thinking, okay, do $1 for the tails. Does that work out? We go ahead and multiply these two. So if we did 100 plays, we would expect you to lose $50 and we would expect you to win $50. So on average, we would expect you to come out even. So that would be fair. All right, so that's a very easy example with heads and tails. What about if we roll a die and now you're betting $1 on just winning if you get a 6, all right? What is a fair wager for him to make on the rest of the outcomes? So the outcomes are 1 through 5 and 6. If 1 through 5 come up, you lose $1, right? What should the pay be? Well, let's look at the probability for you losing $1. 5 out of 6 times you're going to lose $1, which means 1 out of 6 times you're going to win. If we did 60 plays, we would expect, and so those probabilities add up to 1. That's important. If we did 60 plays, we would expect you to win, to lose 50 of them. So you'd lose $50. That's a lot. And we would only expect you to win 10 of them, right? So we should get a total of $0 if it's a fair game. So if you're losing $50, how much money do you need to make on the other 10 plays to come out even? Well, you would need to make basically $5. So $5 would seem like a fair bet on 1 to 5 to match the $1 on the 6 bet, because then you would expect to lose 50 and gain 50 over 60 plays, so you come out even. What this is called is a probability model with random variables, where we have a quantitative variable here and a probability associated with it, and we have different values for this. So the outcomes of plus $1, minus $1, or plus $5 are all random variables. And they're denoted by X, Y, or Z, or some other capital letter, or you can even use a word. So it doesn't have to just be, X, Y, or Z. Random variable assumes any of several different values as a result of some random event, whether you're rolling die, flipping a coin, whatever. Discrete random variables take a value which can be counted. So like the example we did with the wagers. Continuous random variables can take any value in a specified range. And we're going to talk just a little bit about continuous, but today we are focusing on discrete. But at the end, I'll talk just a little bit about continuous. So creating a probability model, the collection of all the outcomes and associated probabilities, usually organized in the form of a table or a tree diagram or a formula, all right? For the probability model to be valid, the following has to be true. All the probabilities have to be somewhere from 0 to 1. So it can be 0, it can be 1, but it can't be 1.2 and it can't be negative. In addition, the sum of all the probabilities must equal 1. If it doesn't add up to 1, you either have a miscalculation or you left out an outcome. All right, so we're going to consider a dice game where there are no winnings for rolling a 1, 2, or 3. And you get $5 for a 4 or 5 and $50 for a 6. So we're going to create a probability model for this, all right? So there's your winnings is $0, $5, and $50. What's the probability that you'll win 0? Half the time, because it's 3 out of 6 rolls. How about $5? Well, there are 2 out of 6 equally likely rolls, so about a third. And for the $50, it would be 1/6. All right. So we know that this model's fine because the probabilities do add up to 1. And just to let you know, you can write it as P of $50. That's the same as saying P of X equals $50. So just a little notation advice there. All right, so now I'm going to give you a probability model that I already put together. And I create this 5-question quiz. And, some kids don't study sometimes. I know, right? And I determine the probability that a kid who didn't study, who knows nothing, What's the probability they get a certain number of questions right on my quiz? All right. I did actually use a technique to do it, but I haven't taught that to you yet. And I actually adjusted the numbers a little bit. All right. Is this probability model that I put together valid? Now, don't worry about the technique I used. All we're checking is, does it follow the rules? First of all my probabilities are between 0 and 1. I could have had a 0, and actually in real life, if you calculate it, that's pretty darn close to 0. So you're guessing 5 questions right on a multiple choice quiz, getting them all right? Not so hot. So let's check the other part. Do these all add up to 1? Well, we add the 0.24, 0.40, 0.25, 0.07, 0.03, and 0.01. Yes, they do add up to 1. Now, for this quiz, we're going to say a student who gets at least 3 questions correct passes. So what's the probability a student passes? Well, that would be these kiddos right here. So we just add up the probability for getting 3 right, 4 right, or 5 right. In this case, we would expect 11% of kids to pass this quiz if they were just guessing. Okay, what is the probability that a student gets more than 3 questions right? So actually pay attention to these words. At least 3 includes 3. So you'd be doing 3, 4, and 5. More than 3 means we're limiting ourselves to just 4 and 5. All right, so I would just add those probabilities for 4 correct questions and 5 correct questions. What's the probability that a student gets at most 2 questions correct? So that means 0, 1, or 2. So I would add up these 3 probabilities right here, and it would be 89%. What is the probability that a student gets less than 2 questions correct? Well, the less thans are 0 and 1. All right, so 64% of the time. So a huge, over half the time, a kiddo's not even going to get more than 1 question correct on this quiz. All right, so let's say I wanted to know how many on average questions do I expect a student to get right on this quiz? Well, we had the probabilities just now, right? But there is a way to predict the average. Let's just start by imagining 100 students. So if 24% of the time my kiddos get none correct, I would expect 24 students to be in that category. And then 40 for getting 1 right, 25 for 2, 7 for 3, 3 for 4, and just 1 kiddo to get all 5 right. So I could just say, okay, let me just count up how many total correct questions there are. Well, for the kiddos who got 0, that's still 0. For the 40 kids who got 1 question right, that's 40 questions that are right. And I'm talking about the total here, all right? The 25 kids who got 2, that gives me 50. The 7 kids who got 3 gives me 21. The 3 kids who got 4 give me 12. And the 1 kid who gets all 5 right gives me 5. And when I add those all up, I get 128. So on average, how many do I expect 1 kid to get right? Well, that's 128 spread out over 100 kids, right? So I just divide by 100. So we average this out to 1.28 expected correct answers per student. And this is called the expected value. That means it's a theoretical long-run average value. It's the center of the model. It's like a balancing point. It's not what will happen, it's what we expect to happen. It is denoted by E of x and sometimes mu when you're talking about population mean. And a lot of the times here, because we do the whole distribution and all our probabilities add up to 1, we actually do have a population mean. It is found by summing the products of variable values and associated probabilities. And this is the fancy formula for it that's on your math chart. So now I'm going to interpret the expected value for the number of answers correct on a quiz. So if many students took this quiz and we just guessed, or they just guessed, the average number of correct answers per student is about, notice I underlined the about. We don't say it will be, it is about 1.28 correct questions. Now, do we actually expect a student to get 1.28 questions correct? No, that's impossible. It's just the expected average over many trials. All right, now I'm going to give you a great tool, Staplet. has a discrete variable function, all right? And we can use it to create histograms, and it will also calculate your mean and your standard deviation. So let me go ahead and show you. So basically we go to thisstaplet.com. If you didn't, I showed you where to find it from the main, but if you just put discrete, it'll take you straight here. Put in the variable name and the values. And you'll notice it only starts with 2 rows. So you got to hit that plus button to add extra rows. Since we have 6 outcomes, I actually had to add a couple of rows. All right. And then once I'm done, I click on Begin Analysis right there. And you can see the graph, and I'm scrolling down here. And if you float over the bars, it will actually show you the percentages in each bar. And you have the mean and summary statistics at the bottom. All right. So the mean, here's the summary statistics. Now it's easier to see, is 1.28, which is what we calculated. So that's good. That's kind of the balancing point. So for a distribution, if we know where the mean is, and if we were to graph it, we could actually balance it. If I actually cut that paper shape out, it would balance at 1.28, which is kind of cool. All right, so let's go ahead and describe this distribution using CUS, because we want to be able to describe any distribution. The center, well, we can use the mean or the median, all right? The mean is 1.28 questions correct. The median, how do I know the median is 1 question correct? Well, I got over 20% here and 40% here. So the first 50%, I'm going to hit the 1. So that's definitely your median. I could also figure out that, guess what, 1's Q1 as well. All right. And I bet you that Q3 is 2, just saying. All right, so I could figure out some of my other numbers. The unusual features, not really anything super unusual, no outliers, no gaps, nothing like that. I would definitely say unimodal, just 1 peak, and definitely skewed to the right. All right. The standard deviation, since I have it, is 1.059 questions correct. So use the standard deviation if you have it. I could do min to max. In this case, I know it's from 0 to 5. And you see how this thing does sort of center on your point. And that's because it's trying to simulate continuous as well with these discrete numbers. So that's fine. All right. So now let's go ahead and go back to our dice game. All right, and we're going to go ahead and practice by calculating the expected value for this one. So we have these values from before, which add up to 1. I'm going to just multiply them across. 0 times 3, 6. 5 times 2, 6 is 10, 6. 50 times 1, 6 is 5, 6. So the expected winnings on this is $10, all right? So let's interpret the expected value. Over many, many plays, we would expect the average winnings to be $10. So we would expect the average to be here. Notice nobody wins $10, right? Because they either win 5, 0, or 50. But on average, we expect them to win 10. Now you could say, well, Silverman, that's not a very symmetric graph. Why are we using the average instead of the median? Well, first of all, the median is $0, right? But if I were, let's say I was doing the game and I was trying to figure out how much to charge for a ticket or budget how much money people are going to win, if I use the median in this case, I'm going to assume it's $0, right? But the mean helps me figure out over many, many plays, we can kind of budget for a total. All right. Now let's get to variance and standard deviation. So standard deviation of a random variable, sigma of x. Now we've seen S of x before. Sigma of x is for a population. And it measures how much the values of the variable typically vary from the mean in many, many trials of the random process. And there is a formula. It's x minus mu, so it's each value minus mu, and I'll show you in a table. Actually, we'll show you in a calculation here, times the probability for that particular value. And this symbol here means sum, sigma, added up. Oh, and by the way, this is also called sigma. Is that not too confusing? It's horrible. So this is actually the variance, which is sigma squared, not to be confused with standard deviation, which is just sigma. All right, so let's go ahead and do the calculation first for variance, because that's easier. This formula is written for variance. So sigma squared, the variance, My first value was 0. My average was 10. I'm going to square it, and the probability of getting 0 was 0.5. My second value was 5. Subtract the mean, square it, and the probability of getting a 5 was about a third. All right. It was a third. It's about 0.333. All right. Then my last value was 50. Subtract the mean, square it, and multiply it by 0.167. And I get an ugly number, roughly 325. Well, I can take the square root of that to get the standard deviation, and it's about 18.03. So how do I interpret this? This is where this piece comes into play. The winnings typically vary by about whatever the standard deviation is from the mean. So by about $18.03 from the mean winnings of $10. So that tells you about how much it varies. All right, on average. Okay, you can also use it for the table. So like that calculation where I did the difference there and squared it, and then just multiply it by these probabilities here, and then add it up, and then take the square root. So you can also do a table. But I will say the Stapplet does calculate it automatically.